All right, we're recording and ready to go. So Tuesday. All right, so here's agenda. I'm going to run attendance here in a couple minutes. While I'm doing that, I have a fun problem from your guys' college textbook right here. It has to do with the bridge in Bosnia. So let me read this real fast and then go over the rest of the agenda so you guys get to think about this a little bit. It says in Bosnia, the ultimate test of a young man's courage used to be to jump off a 400-year-old bridge. Ooh, and then a little bit of history there. Into a river 23 meters below the bridge. Youch, that is a long jump. Basic questions are, how long did the jump last? Do you guys think if you knew how far you were falling, like 23 meters, there's some specific time that is associated with that time of fall, right? On Earth? Next question, how fast was the guy splashing into the river? Okay. And then, and you can figure that out too, right? And this question falls a little more complexity. It says, if the speed of sound in air is 340 meters per second, because sound travels really fast, right? Then how long after the jumper jumped off the bridge did a spectator on the bridge hear the splash? So let's say you're his friend, also standing on the bridge, the guy jumps off, there's that time to fall, but then also the time for the return trip of the sound, right? So what's the total time waiting for all that to happen? Right? Right, so think about that a bit. I'll show you guys how this is related to measuring your own reaction time. There's a lab sometimes I do with students, but I'll just show you guys the right on the top to you. It's very similar to this problem. Okay? I'll go over, there's some follow-up I wanted to do from yesterday, just hit a few points, including I want to show you guys the solution to that homework assignment that I gave you. The homework assignment that I gave you, you remember what I want you guys to do was for some alien planet where you don't know the gravity, but you do know that you have a cliff of known height, and you know your throwing speed and the crashing speed. Maybe somebody brought a radar gun so they can grab these two numbers, and somebody brought a meter stick so you can grab the height of the cliff. Can you figure out the gravity pull of the planet and also how much time it would take to reach the bottom in terms of the variables? Okay? So I'm not looking for any numbers here. I'm just looking for the solution, like a very generic formulaic solution. Okay? But I'll show you guys one for there. Right? I had a couple of questions on AP Classroom from yesterday, so we'll take a look at those real fast. And then our main thing that I want to get to today that's going to take most of the class is going to be a linear motion lab involving a toy car in an incline. So we're going to do that. We're going to get to talk about some graphs related to this too. One of the assignments that's on AP Classroom is an FRQ. I wanted to get to that today, but we're going to have to postpone this. So we're going to postpone this one to Friday. Okay? Or at least that's the tentative plan. Right? So I know right now it says due Thursday, but hang tight on that. Okay? So don't do that. I'll show you guys in class what I want you guys to do by tomorrow. Okay? Right? So you guys good so far? Right. So while I'm running my attendance, see if you can solve that bridge question.
I just designed things for homework. I just didn't see the problems with connected, so I was to see Davis yesterday. Do you want me to make up the homework from last night and anything?
Yeah, just write that note on the paper, okay?
Okay.
Make sure I got my tenants right. I think there's Zoe Griffin is absent, but I think we've got everybody else. I think that's right. Got everybody? Except for one absent. All right. So yeah, let's get rolling on this. We'll talk about Virgin Bosnia, related activity you can do, and then go over the solution on the homework. Okay. So did anybody figure out how long the jump was going to be? You figure out how long the jump took to fall into the water? Yeah. 2.1? You guys can say about the same thing? That sounds about right. 2.1, 2.2, somewhere there. Right? And ooh, I should have thrown you guys' formulas up here. Okay. But you guys do have these on AP Equation Bank anyway, even though they're written a little differently, but you could access them there. Or actually, I do recommend that you memorize them because they could help you navigate them. But which one of these did you use to solve for that? First, second, or third? Yeah, I like the first one too, because you know the height of the bridge, x, and you want to know t time, right? And that's the only one that has both of those in it, so that's really opportune. Also, it's really nice and convenient that, what is v naught in this situation? 0. It's implied to be 0, because if you just like step off the bridge, your initial velocity is 0, right? Okay. Aha, yeah, let's do that. And so we got, so it really just boils down to this. Right? So it's like a simplified form of it, right? This would be true at v naught is 0 meters per second. Okay, like that. Okay. Oh, I should get a picture going. Okay, let's get a picture. Let's say there's a bridge up here, there's some water down here, okay, got some fish. Ooh, guess this fish is about to get jumped on, it's about to get a fish to a prize. And we know the height of this thing is like 23 meters. I'll just call it some generic x. Okay? We know that v naught is 0. And we also know the gravity pull, right, which is like 10 meters per second squared, because I only know one planet that has bridges on it. So let's pop that stuff in. Okay. Now, actually, the way I'll solve for this first is I'm going to solve it in terms of the variables, kind of like the ones you guys can do on your homework, so you get a little practice with this. Okay. I kind of come up with some generic solution, so I could solve for like any bridge of any height, right, or something like that. So say I need to cross multiply the 2, divide the g down. So 2x on g would be t squared, and then take the square root to solve for t. Wouldn't that be true? So you get t is equal to square root of 2x on g. Right? Now that's a good generic solution. Right? Ooh, I like that. Right? That's what I was aiming for you guys to do for your homework. Right? Let's plug in the specific values that we have. We've got 23 meters, 23 meters. And we got 10 meters per second squared. That's Earth. So I'm getting, what's the square root of, okay. Now I gotta be careful, square root, I'm gonna open up another parenthesis. This is just a little calculator trick. See, watch this. Here's how I can do it wrong. You wanna see something wrong? 2 times 23 divided by 10. Okay. Oh, 3 seconds, that's not what you guys got. This number's wrong. You know why? Because how I plugged in, as soon as I close the parenthesis, the calculator stops square rooting. So scroll up, scroll over, insert a parenthesis. Okay. That's what you guys got. 2.14 seconds. You guys see that? Okay. That's it. Now, I should pause and say too, really, if I got a 23 meter tall bridge and we're using 10 meters per second squared, how many sig figs am I really allowed to work with? Probably 2. Yeah, I see you guys saying 2. Right? So really, I should say like 2.1 seconds. Okay? AP is not a big stick, at least AP physics is not a big stickler on sig figs, so they would take this. Yep. Yeah, like almost all the time we'll use 10 in here. Yeah, you're right. I like, you can use either on the AP exam. They tend towards 10. There's a lot of reasons I like 10, so I'm going to usually stick on 10 meters per second squared. Okay? All right. Then you're supposed to figure out how fast was the guy splashing into the water. Let's go back to equation shopping to figure out, ooh, that'd be like final velocity, wouldn't it? Now, we've already exhausted the first formula. It doesn't say final velocity anyway. Which one do you guys like for the splash speed? The second or the third one? Yeah, the second one? I do too. Let's do that. Okay. Now, you could use either one. Right? See, the third one you could use if you plug in the direct height of the bridge. The second one is a function of time, But we have that number anyway because we just found it. Right? So let's do that. Right? Oh, and I want to keep that, see that 4 is kind of fuzzy. Like, do I really know it? I'm not, but I'm going to keep it for calculation purposes and then round it again. So we'll do it. Let's go. So that was part A. Part B is going to go final velocity is equal to initial velocity plus AT. Well, of course, this number is just 0 anyway. So it goes away. So the splash speed is, I got 10 meters per second squared times 2.14 seconds. Right. That's going to give me 21.4 meters per second. Or really to choose figs, I could say about 21 meters per second. That's what you guys got too, right? You guys got about that one? Right? All good? All right. Then finally, part C, if you know the speed of sound, then you guys remember this jumper has a buddy in here. Right? Let's say his buddy has a stopwatch, and let's say he's also wearing a blindfold, like a bird box or something. And he starts the stopwatch as soon as this guy steps off the bridge, and all he's doing is he's listening for a splash. So the guy goes, to splash, and then it takes time for the sound to return, maybe a little time delay, right? Yeah. Do you guys think that time or the speed of sound is influenced by gravity, or do you think it goes constant speed? Constant speed, right? So we're gonna do something with like distance equals speed times time. Okay. So part C. Okay. Let's just figure out the return trip for the sound. Maybe I should do something like distance equals speed times time. Would that be true? Okay. Now this is okay as long as acceleration is 0 meters per second squared, which it would be for sound traveling because there's no gravity influence over sound, right? We're solving for t. So in terms of the variables, it would be this, wouldn't it? This and this say the same thing. Okay. So what did you guys get for the return trip sound? You figured it out already. Anybody get that far? Yeah. What'd you get?
0.07 seconds.
Kevin got 0.07. That sounds about right. Okay. Let's see if I get the same thing. So it's 23 meters. The sound travels constant 340 meters per second. The speed of sound. Well, at some certain temperature it is. Okay. 23 over 340. Yeah, I got. I think that's what Kevin got, right? So 0.06. Round a little bit. Something like that. A little bit of time. Okay. Now that's just for the return trip of the sound. Okay. But if the guy is, like, if you read this very carefully, it says, how long after the jumper took off did the spectator hear the splash? Okay. So it's not just the return trip sound, it's also the guy following. You have to add that in too, right? And the falling time was this right here, 2.14 seconds. You guys remember? Okay. So let's see, if it was 2.14 seconds to fall and a tiny blip of time for the sound to return, shouldn't I add those two times together to get the total? Okay. So plus 2.14. One thing I really like about this calculator is you can just say plus and it'll pick up from your last answer. It'll say answer plus. So 2.207 something, we'll call it like 2.217. Right? Or if I'm really allowed to only work with 2 sig figs, I'm saving my rounding for the end, it'd be about 2.2 seconds, wouldn't it? Okay. So, okay. So I'd say it takes about 2.1 seconds to fall and about another tenth of a second almost for the return trip. Okay. Got good stuff. All right, Bridge in Bosnia. Now that is related to a lab that I sometimes have students do, but I'm just going to sketch this out for you guys. You see it says how to measure your reaction time. Okay. There is a certain delay between what's going on in the outside world and your perception of what's going on. Okay. There's a certain time delay between like me speaking and your brain processing the words that I'm saying, right? Or if you're driving a car, someone steps out in front of you, you slam on the brake as soon as possible. Well, there's a certain delay between you recognizing something and slamming on the brake. Right? What is that delay? Well, you can't perceive that delay because that delay is like built into your brain, right? So, like if, and how could you measure that time delay? Could you use a stopwatch to measure that time delay? No, because like using a human to measure human error time, well, that's kind of right, the problem we're trying to solve, right? I guess if you had like maybe a slow motion camera and you did something like 3 seconds, like, boom, and you're like, oh, if you have like a slow motion camera, you could probably figure it out frame by frame. But there's a simpler way, okay? And your measuring tool is this right here, a ruler. Okay? How can you use a ruler to measure your reaction time? What do you think, Jared? Yeah, right. someone drops it, someone tries to catch it. What if you orient your ruler this way? And let's say you have your fingers right here, like finger, thumb, like you're just like ready to catch it. Okay. And there's someone up here who's punching the ruler. Okay. So they're holding it right here, like this. Okay. And this is the 0 centimeter mark. And this person holding the ruler on top, just like surprise drops it, and this person bottom catches it as fast as they can. Okay. Now, are you going to catch it at the 0 centimeter mark, or do you think it's going to fall a little bit? It is going to fall. And do you think that's directly related to, or related to your reaction time? Okay. Aha, aha. In fact, do you guys think that bridge in Bosnia map that we just did could solve for, oh, look at this right here, that solve in terms of variables. Is this the answer to what I'm talking about? The reaction time as a function of it falling on Earth? That is exactly it, isn't it? We already solved this, right? Guess how this is related to the Bosnia bridge question, right? Okay. So the time for it to fall, your reaction time, since we did the work already, comes out to be this. 2 times the falling distance divided by Earth gravity. That's just the square root of that. Okay, you guys good? Let's plug in an example number. I'll say e.g. It's Latin for some phrase that means for example. So plug in some example numbers. Okay. Do you guys know, some of my students last block actually knew this, what the average falling distance would be if you actually did this experiment? What the average falling distance is for people? About how many centimeters? Who's got a guess?
4?
Okay, I got to guess about 4 centimeters. What do you think?
6.5.
About 6, I got 4, I got 6. Who else has a guess? What do you think, Joe?
We'll just add 2, 8.
8. Oh, yeah. I'm sure there's some kind of psychological bias going on here. I'm sure there's a name for this. Is that everybody's picking numbers about the same number. I think it's called rounding or something like that. Like if you ground a certain estimate, right? It's actually closer to 20. Right? You can try. Go ahead, go home and try this with your friends, with your siblings, parents. Try this out. Right? See what your reaction times are. The average reaction distance will be about 20 centimeters, but we can convert that to a time, right? Let's see what it would be for 20 centimeters. Now, if I'm plugging in G of, let's use a more precise value for G. I won't do this too often, but let's go ahead and plug in 9.8 meters per second squared. Okay? Now, if you do that, remember that units are really important in this class too. So do I want to plug in the number 20 to represent 20 centimeters? Does it have to be consistent with this unit of meters? How many meters is 20 centimeters equivalent to? Yeah, 0.2. Yeah. Okay, so if you drop this ruler and caught it at the 20 centimeter mark, I would say 0.20 meters. Okay, you guys get the idea? Okay. Now, you guys were guessing the average falling distance would be, you guys were saying numbers around like 5 or 10 centimeters. Okay? If you were catching around the 5 or 10 centimeter mark consistently, then I'll tell you what, you have like super blitz fast, like superhuman reaction time if you can do that consistently. So, okay. There's a similar trick people have done like the dollar bill. Like if you hold a dollar bill and you do the same thing, like almost nobody can catch the dollar bill. So it's every once in a while you're not able to. Okay. All right, so let's try this out. So do square root of 2 by 0.2 but divided by 9.8. I'm getting an average reaction time of 0.202 seconds. Right? Yeah, weirdly enough, 0.2 meters and 0.2 seconds happens to correlate. There's no reason for that. It's just a complete random thing. It's like 0.20. You guys see that? Okay, that number. Okay, so yeah, that's the average person's reaction. Actually, I think it's close to like a quarter of a second. So somewhere in there, about 1/5 of a second, quarter of a second. All right, guess it? Okay. All right, you guys want to see the solution to your homework? Let me switch some papers here. Okay. Right. Now, I did say that I was referring to a particular story, which was number 17, number 18. It says you're on an alien planet and blah, 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 and I gave you some numbers. Okay. But then I just read you it here. Okay. Even if you didn't have that paper, like if you had lost it or turned it in, all you need to solve this is what's written up there, which is what I showed you guys yesterday. Okay. All right, so in general, you know this, right? You're on a cliff of some planet, you don't know what the gravity is, because some alien planet. Right? But somebody brought, you have 2 instruments. You have a radar gun, so you can grab these instantaneous speeds, and you also have a meter stick, so you can grab the height of the cliff. Okay? So can you make some general way to solve for the gravity of this planet? Maybe you jump around many different planets, so you're doing the same experiment over and over. Can you solve the gravity And then furthermore, can you solve the time based on these three known quantities? Okay. You guys get the idea? Okay. Once you got that premise, this is really just an algebra problem. Okay. So let's take a look at those three formulas. So if you know everything except for gravity and time, right? One thing I'm thinking, because we're trying to go equation shopping, right? Trying to get a foothold, where should we start on this thing? Every single one of these formulas has which variable in it? Yeah, they all have something like this acceleration value, like gravity. They also have V naught. Okay? But yeah, they all have the acceleration. So let's solve for that first. Right? Now, we don't have time. Nobody brought a stopwatch, right? Nobody brought a stopwatch, right? At least in this story. So, which one looks most opportune, first, second, or third? I hear a bunch of guys saying the third one. I like the third one too, because the first two involve time also. They each have two things that we don't know, the A and the T, right? But the third one has only one unknown, which is just the acceleration value, the free fall gravity. Yeah, let's do that. So let's go, the final velocity squared equals the initial velocity squared plus 2ax, where x represents the height of the cliff. A is the free fall gravity. Okay? So this is just algebra. Can you rearrange this and solve for A? So I'm going to subtract over V naught. So I'll go Vf squared minus V naught squared. Okay. So that's 2ax. And then just divide both sides by 2x, right? You see that? Okay. So Vf squared minus V naught squared divided by 2x. That's the free fall gravity. So you can say equals A or equals G. Either way. There it is. That's the answer to number 18. Okay? And then I did give you specific numbers on that page. So if you went ahead and plugged in those three numbers, because I gave you Vf, V naught, and x, could you just plug this in and figure out the gravity on like any planet you did this experiment on? Yeah, sure could. Okay. And then notice how I numbered this. I said do 18 first and then 17. That was a hint because that's the easiest way to solve this, is to do it in this order specifically. Okay? So can you figure out how much time it would take in general? And look, notice it's also in terms of the same three variables. Okay? So if you do this completely correctly, then your answer is going to be in terms of V naught, Vf, and x. Okay? Okay. So we need something to do with time, right? Something to do with time. Now take a look at those three formulas. And if we're trying to solve for time, and we sort of figured out acceleration already, then which one looks most opportune, first, second, or third one? Ooh, I hear a bunch of nominations for the second one. I like the second one too, because there's a T here. Now, could you do the first one? You could, but you would run into what situation starts with a Q? Quadratic, yeah. You guys want to do quadratic? No, we ain't got time for that, but you guys know that, right? Okay, so let's do the second one. Yeah, let's do it. So I'm going to go, so this is number 17. So velocity final equals velocity initial plus acceleration times time. Okay? And so we're trying to solve for time on this one. Okay? In terms of Vf is fine, in terms of V naught is fine. But acceleration, isn't that this whole box value right here? Can I just substitute that in there? I call it, say SUV for substitute. Okay? Okay, let's do that. So final velocity equals initial velocity plus, oh boy, I got final velocity squared minus initial velocity squared divided by 2x. Right. All times what I'm really interested in. Okay. So T, we've got to isolate that. So again, this is mostly algebra at this point, right? Okay. So I see a few terms here, boink, boink, and then crazy boink. I'm going to subtract over the V naught. So I'll go the difference in those two velocities is equal to crazy fraction times T. And remember, at the end of this long process, I want to isolate T. I want it to be like T equals something, right? Kind of like I did for acceleration up here. Acceleration equals something. T equals something. So continue this process. Oh, do you guys think I should take this whole coefficient, this whole crazy fraction coefficient, and flip and multiply it on the other side? I can do that, right? Yeah, that would isolate T, wouldn't it? Okay. So we did. Here you go. And you may approach this a little bit differently, because there are different approaches you can take. But let me do this. Yeah. Take this 2x, I'm going to cross multiply it up to the other side. And at the same time, I'm going to divide down the Vf squared minus V naught squared. Okay. And that, I have to shove way to the left of my paper. Oops. Okay. That is enough to isolate T. Okay, you guys see that? Okay. Now, if you did this and you got to this point and you boxed in your answer, then I will take that, and AP would take that. If AP asked you that question, then that would be good because that would be the answer. See how time is strictly in terms of the three given variables, x, df, and d naught? Okay? And yeah, we did substitute an a to get to that point, but there's no a or there's no g that's written out there, right? Okay? There is a way to simplify this though. There's another step you could do, and I bet so many guys are seeing it, but it's a little tricky. Okay? Does anybody see how I can simplify that? Oh, I see a couple of guys on. Yeah, what do you think, Adam?
Maybe like subtract the
Ooh. Okay, so you're on the right track, right? Something to do with, there's going to be something that kind of cancels here or something. Now you can't just scratch the exponents right away, but there's something else you can do. Yeah, what do you think I do? What's that? Okay, you're saying back at the bottom, you're going to say,
I was just gonna say that VF and V naught are gonna cancel out because there's two at the bottom. So
Ah.
it would be 2x over VF minus.
yeah, I think Bella's on the right track too. I like the way that Adil, did you say that right? Adil, right? I like the way you said it. You said what you can do is VF minus V naught. You can take this box. This is a difference of squares, isn't it? Okay? You're saying you can factor this apart, make it VF plus V naught, VF minus V naught. Can you do that? All right. Okay. This, if you FOILed it, it would bring you back to this, wouldn't it? It's a difference of squares. It's a good math trick to know. Right? Again, if you didn't know that, you just got to this point, then that's perfectly fine. But if you do this, now that cancels with that, doesn't it? Chuck, chuck. Isn't that be true? Right. So more simply, I could say just plain 2x over the sum of the starting and ending velocities. That's what kind of simplifies down to like that. There's lots of steps. Right, so if you got that, and that's what you turned in, then that is a 100% credit. Okay. Now, I'm going to guess that some of you guys didn't get to that point for whatever reason. Maybe there were a few students that weren't quite clear on what was going on. So I will give you guys a redo option. Okay, you guys ready for the redo option? And so redo option. Okay. Now, they said if you did everything 100% right, then you don't have to worry about this because you're good to go. Okay. But if you're thinking, okay, I flubbed that one for whatever reason, okay. Then so same, I'm referring to the same page that I pulled this off. Let's do you guys see number 7, number 8? Number 7 and number 8, which also involves an alien planet. Okay. Let's say this time okay. A little bit different set of things though. Okay. You know the height of the cliff on the alien planet? This time somebody did bring a stopwatch, so there's some time t. Okay. And you know that V naught at the top of the cliff is 0, you just drop it like that. Okay. Can you solve for both acceleration and also final velocity in terms of these other three things, in terms of V naught, X, and T. Okay? Okay. So if you want to go for the redo option, then if you're in class, then you can throw this in the grade tray tomorrow. So it'd be just like what we just did, just a bunch of algebra mostly, set up, just rearrange things. Okay? If you're online, then look for a place to upload it on Focus. I haven't created that column on Focus yet, but I'll get that really soon, definitely by the end of today. Okay? So you can upload it to Focus and do the redo. Okay? You guys good there? All right. Let's see what's next on my list here. I got that. Get these pages somewhere. I'm not going to lose them. Okay. Okay. There was. We're getting really close to the lab, but there's one more thing I want to slip in right before we get rolling on the lab, okay, and that's going to be. I got to. Let's look at a couple of these AP classroom questions. Okay, now let's get ready for that yet. Okay. AP loves to log me out. Okay. Go to AP Classroom. Okay. Then just right. Right there. Oh no, what's going on? I just want to look at a couple of these because I gave you guys hints and pointers for a lot of these yesterday. And then stopped at some point and I got a couple questions about ones that were coming up. So I want to give you guys a couple pointers on just like two of these. Oh, come on. Okay. What the heck? Check. MCQ. Alright, so I think this was the next one coming up, right? Number 11. I haven't talked about this one yet. Okay. So we got this weird system. It's going to slide without friction down this incline. Actually, pretty similar to the lab we're about to do. It's not too far off from what you're about to see in class. Okay. And they give you a velocity versus time curve for the center mass between these two things. Okay. So if you focus on the dot as it's sliding down, okay, there's a velocity versus time, like how fast is a function of tick, tick, tick. And then if you read this question, it says, how much time would it take object X to cross point J? You guys see object X and point J? Right? The question is how much time would that take? Right? Let me ask you guys a different question. How much distance would this thing roll down for object X to exactly align on point J? How much distance? You guys see 9 meters? You see 9 meters, right? Okay. Right. But the question is how much time would that take? Right? Do you think it's somehow something to do with this graph? Right? Now, you guys know it went 9 meters for this all to line up right? 9 meters? What property of a velocity versus time graph would tell you 9 meters? Lily's saying area under the curve. You guys get area under the curve? Because area under the curve represents some number of meters, doesn't it? Right? Meters per second times seconds gives you meters. Okay? So can you guys imagine as you're going left to right, there's like triangles so you can get bigger and bigger? Like after 1 second, this triangle represents how far it's rolled. After 2 seconds, this larger triangle, right? You guys think there's a triangle that represents an area of 9 meters? Right? You guys can figure that out. Right? And let me give you pointers on one other one. The next one, we've got 2 cars, like car X and car Y, and they're doing this, and we got, it's another velocity versus time graph. Man, there sure are a lot of velocity versus time graphs. Okay. And then they give you 4 statements, and they want you to figure out which statement is true. So it's like 1's true and 3 are not. Okay. But you really have to understand what's going on and parse out these details. Okay. So let's, and I forget what the options are, but I don't really care. I'll let you guys figure that out. Okay. But let's see if we can sort of make sense of this graph anyway. Okay. So let's start with car X. Car X is this dashed line, isn't it? So at time 0, is car X starting from rest? Yes, it is, because it has 0 velocity at time 0, right? And then after that, what is it doing? Is it moving forward? You know it's moving forward because the velocities are positive. Is it going constant velocity? Or is it speeding up? It is speeding up, isn't it? Because this velocity curve has a slope. Now, slope would be acceleration, wouldn't it? It's going faster, faster, faster. So it's speeding up, right? How about car Y, right? The solid line car Y. Does car Y start from rest? How many of you think car Y starts from rest? Oh, nobody says car Y starts from rest. Car Y starts with really fast velocity. And after that, what is car Y doing? Speeding up or slowing down? Slowing down, right? Because velocity is getting less and less and less. Is car Y still moving in the forward direction? Yes. How did you know yes? Yeah, because all the velocities are positive values. They're all like positive coordinates, right? Now, there's something negative, the slope is negative, but the negative slope refers not to velocity, but to the acceleration, yeah, right? So negative acceleration. But the positive velocity is still moving forward. Both these cars are moving in the forward direction, right? One speed up, one slow down. What about this point where they cross? Where they cross, that means they have the same what? Same speed or same velocity, yeah, right? Be careful, because maybe some of these trick questions are trying to lead you in the wrong direction, possibly about that intersection point. Okay? You guys good? Okay. There's a couple points there. Okay. All right. Let's jump over to the lab. Okay. So Oh, I should have showed you guys this paper at the top of the class, but you guys at home, I mean, I did tell you guys we're doing the carbon ramp, like, carbon ramp lab anyway. Okay. So, print this out at home if you haven't yet. Everybody in class has one of these, right? You guys got a couple of tables side by side? Right. And what I'm trying to figure out, or what we're going to do, is here's the setup. Okay. I'm going to have a toy car at the top of a ramp, some length, and you need someone to time. Okay. So I need a couple of helpers today. I just need someone to run a stopwatch and need someone to have a calculator to take some averages. Okay. So who wants to run a stopwatch? Who volunteers for a stopwatch? Okay. Joshua, you have a stopwatch function on your phone? Yep. Okay. All right, so pull that up. Okay. And I need someone to calculate some averages. Who wants to calculate some averages? Okay. All right. Yeah, Morgan, okay. You got a calculator? All right. Cool. Okay. So I want to know what's the relationship among these three variables. Like, for example, if I change the mass of the car, that could maybe possibly, let's say I control like some length, like it's going to go so many centimeters. Right? If I make that car heavier and heavier, just throw this out as a question. How is that going to affect maybe how much time it takes for the car to roll down? Right? Let's start with that question actually. Let's do a quick hypothesis. Because there are three possibilities. As they make the car more and more massive, and they'll do that by taping masses onto it, like little lab weights. Right? Because as they make the car more and more massive, one possibility is that it's going to take the car longer to reach the bottom, like it'll slow down. Second possibility is maybe it'll make it sit down faster, like more massive, like faster. The third possibility is maybe it makes no difference at all. Let me see show of hands what you guys are thinking. How many of you think if I take more mass into the car, it's going to make the car go slower down the hill, slower? Who says faster? It's going to sit down faster. Ooh, like I said that. And who says it's going to make no difference at all? No difference at all. Okay, so there are different hypotheses going around, right? I should show you guys the materials we're working with too. Right? So we got a toy car. Yeah. Okay. So for you guys at home, here's the toy car we're working with. It's 30 grams. Okay. We got a meter stick to measure length. We got an incline. Well, I better have a protractor to measure the incline of this angle, the angle of this incline. I care about that. Here's some weights that'll be taken onto the car, little lab masses. Okay. And then Joshua's got the stopwatch function, and Morgan's got control of the calculator. All right, so set this step aside. All right. But maybe there's also a relationship between x and t. Right? What if I leave the mass of the car the same, just maybe a blank car, right? But I vary the distance. Right? Now, obviously, if the car has a longer distance to roll, it's going to take more time, right? But is that relationship going to be linear or non-linear? Like, for example, if I double the distance from 100 centimeters to 200 centimeters, would that double the amount of time that takes for the car to roll down, or is it going to be something different than double? Okay. Let's just have this be the two hypotheses for now. Okay. How many guys think if I double the distance, it will pretty close to double the time, like double? Okay. How many guys say it's going to be something different than that? Ooh, okay, yeah. Right. Right. So now, I should tell you guys for context how AP is ideally supposed to work is that I'm supposed to throw you a question like this, like what is the relationship among three variables? And then I give you guys like all these things like, oh, here's a mouse, and here's a car, and here's a ruler, and here's a protractor, and go figure it out. Okay. But between the time crunch and the quarantine, we're gonna just do this a little different. Tell you guys where we're headed with this. Okay. So guys, in an experiment, ideally you want how many independent variables at a time? One. I see you guys saying one, right? I see one. See Eric up here saying one. So we can't do this all in one experiment since we're trying to juggle three variables. What we have to do is break this into two different experiments and control for one thing at a time, okay, and have one independent variable that we are personally changing. And what we're going to do is treat time as the dependent variable to see like how the car rolls, grab some time values, see how this all plays out. So in the first experiment, we'll control for the distance the car rolls, same distance over and over, okay, but we'll vary the mass of the car. Okay. And then in the second setup, we'll control for the mass of the car, but we'll vary the distance of the car rolls. Okay. So on this lab page, you guys got your name on this? Okay. Let's first control for the distance. I'll let the car roll 200 centimeters, and we'll do that all the way down. So 200. Oh, by the way, today we're using grams and centimeters. I know we don't traditionally use that, but they'll be perfectly fine for today's lab. Okay. So 200 centimeters. Okay. The mass of the car, I should have a scale up here. Oops, but I did measure the mass of this car ahead of time, so it's 30 grams. So the blank car is going to be 30 grams. After that, I'm going to tape on some masses. So think on that. All right, you guys okay with those setups so far? Okay. Another thing I need is to grab this angle. So I'm going to do that here up front pretty soon too. Okay. All right, I need to do something tricky here. I always have to think really hard on this. We're gonna do a little switch. All right, for a lab setup. Again, the way we're doing this lab is not the traditional way of doing things, but we're gonna do what we got to do here. This. All right, so I've got, here's this incline. Now you guys see how this incline has basically a meter stick attached to it. Right, so we can measure it in centimeters or meters, how far something's rolled. So I'm going to put the 0 mark down towards the wall. I'm going to prop this up. And then the toy car, here's just the basic mechanics of the car. Here's my toy car. It's going to roll down. Oh my God. Okay, that's the gist of what we're doing. Okay. And then we just got to grab some measurements. Okay, so Josh, you got the stopwatch ready? Right? All right. So first we start with just a blank car, which is 30 grams. We're going to go from 200 centimeters. Okay. Hold on a minute. Yeah, that's what we're doing. Okay, right, ready? Right, I'll do a countdown. Okay, ready? Actually, let's do a trial run first. Okay, so 3, 2, 1, start. How long is that? 1.38. Okay, so let's call it the trial run, and we'll start grabbing data with this one. Okay, ready? All right, 3, 2, 1, go. 1.21. Okay, so measure time 1.21. Now, you notice on your page there's actually 3 boxes there, aren't there? Okay, so we're going to do 3 trials and take an average. Okay, ready? 3, 2, 1, go. 1.18. Okay. And last one. Okay. 3, 2, 1, go. 1.22. Okay. And Morgan, what's the average of those 3? 1.20. Okay. And then if you square that, you guys see the column next to it says average time squared? If you square that number, what do you get? 1.45. Okay, okay. Now, this shouldn't make any sense yet, y squared, but I don't know, maybe you can figure it out. But why are we doing 3 trials and taking an average? Why not just do 1?
Reliability.
Yeah, more reliable, more accurate. There's a specific kind of error that we're trying to get rid of. Let me see if you guys can figure it out. Just different kinds of error. Let's focus on systematic error versus random error. Okay, so systematic error is like something built into your instruments. Like for example, if you always start stopwatch early, and it's just part of programmed into your brain, you're someone who always starts first early, right? Random error is like, well, sometimes it started a little early and sometimes it's a little bit late. Okay. Now, by taking 3 and taking an average, which of those errors are we specifically addressing? The systematic or the random? The random. Oh yeah, you guys are on. Yeah, you guys see it would be random error, right? Yeah, awesome. Okay. So we can get rid of that. Let's take on some mass. I'm going to find a 50 gram mass. Okay. I'm going to take the 50 gram mass onto a 30 gram car. So what's the new mass? 80. Yeah, so go 1 cell down under the mass and put 80. Okay. So we got a 50 gram mass on a 30 gram car. Okay. But we're controlling for the rolling distance. Okay. So it's still going to be 200 centimeters. Okay. You ready, Big Josh? Okay. All right. 3, 2, 1, go. 1.17. 1.17. Huh. It's really somewhere there. Look at the first round. Oh, yeah. Fun is the right word. I think this class is pretty fun. You guys think this class is pretty fun?
Yeah.
Yeah, I like solving these problems. All right, ready? 3, 2, 1, go. 1.41. Okay. And ready? 3, 2, 1, go. 1.23. All right. So we're done with that one. Real fast for everybody online. Just my checklist what we got so far. Okay. So we got it. You guys in class, it's all mirrored, but everybody at home, I think that should make sense. Okay. If you screenshot that or something. All right. This is what we got so far. Okay, so I'm pulling off the 50-gram mass. Okay. Let's tag on a 100-gram mass, which brings you up to 130, wouldn't it? Right? 100 grams plus 30 from the car, that should give me 130. All right, 130. Okay, ready to go? Okay, 3, 2, 1. 1.19. Perhaps they go, but you got it on the beat. All right. Okay. 3, 2, 1, go. 1.06. Oh, man. And choose the most breakable tape that I have with a poor choice. Okay. And 3, 2, 1, go. 1.40. Right. Oh, Morgan, I forgot to get the averages from you and whatnot. What was the average of the last three sets?
1.27.
1.27. And what's the average of the ones that we just did?
1.22.
1.22. Okay. And then if you square 1.27, what do you get?
1.61.
1.61. If you square 1.22?
1.48.
1.48. All right. Nice. On top of that. Okay, so quick check in for you guys online. Screenshot, whatnot. That's what we're looking at. Okay. Let's do a couple more rounds here. 49. Okay, yeah, we're done it. Okay. Okay, so gonna take off this 100 grammer. And let's bring in 200 grams. Okay, so we're gonna have 200 grams plus the 30-gram card. That brings us up to 230. Okay. So the mass is going to be 230. Right, so 230. Ooh, hold on. Okay, yeah. Okay, right, ready for 230 grams? Okay. 3, 2, 1, go. 1.14. Okay. Ready? Okay. 3, 2, 1, go. 1.42. And 3, 2, 1, go. 1.31. Okay. So, Morgan, what is the average of those three?
1.29.
1.29. And what's the square of that?
1.67.
1.6. 1.6 something? All right. Okay. And last trial run. Let's go big and go home on this. Let's go 1,000 grams. You guys want to see 1,000 grams? Maybe. We might be seeing into the.
We still have 2 more columns.
Huh? Oh, yeah. We'll just do 5 5 data points here. Save a little time, but we'll be able to make a graph with 5 data points.
Is it 1,030 grams?
Oh, yeah, you're right. Okay, so it'd be 1,030 grams. Good call. So overall, it'd be 1,030 grams, right? Oh, whoops. I kicked the car upside down. That's going to go anywhere. Okay, well, hold on a minute. Something wrong here. Oh, boy. Oh, yeah. I think it's about to happen. Probably kicking through like the guy from The Shining. Like, ah, you're scrubbing. All right. Hey, get ready? Okay. Okay. 3, 2, 1, go. What we got? 1.45. This is what feels like to bust into a castle. 3, 2, 1, go.
I probably did that earlier because I heard it like.
All right, let's do another run.
I don't think David likes you very much right
That'll be all right.
now.
I don't need to be right. I just need to.
At least it's only one and
That's really close to
one
Georgia.
of us doing this.
Yeah, you can blame it all on me. Yeah, it's all my fault. All right. 3, 2, 1, go. You know what? Let's
1.02.
I like that idea. Let's say we did 3 on that. All right, we're gonna focus a little bit because let's call it 1.45 is the average. That's really what happened. Yeah. All right. Okay, what's 1.45 squared?
2.1.
2.1. All right. Okay. So for a bit in line, okay, this is our data table. That's what we're running with. I know we're taking a few shortcuts here, but we're doing what we have to do. Like I said, oh, I never grabbed that ramp angle that I promised you guys. Let's grab that ramp angle because I bet that ramp angle would be important to the motion of the car, right? Okay. So, you guys were using a protractor in this class back last week. That's how we're going to measure ramp angle. Before I grab the number, if you guys just eyeball this setup, if you had to guess about how many degrees that ramped up, what do you guys guess?
45.
I heard a 20, 30, 45, somewhere there. Well, it's probably less than 45. Like 45 would be pretty extreme, right? I would guess probably about 20 if I had to guess. Ballpark of 20. Okay. So let's see how close. So I'm going to take the protractor, put it flush on the desk. We'll call it desk, like 0 degrees. Okay. Then there are 2 points on this ramp. One will go through this node, and the other will sweep through one of these angles. Okay. Hopefully in the ballpark of about 20 degrees. Let's see. Okay, so be flush with the desk, which is flat. This axis is flat. Go through 15. I'm looking at 15 degrees. That's a 15-degree angle. 15, 1, 5. Okay. Well, what if it wasn't 15? What if it was like half of that? What if it was like about 7 or 8 degrees? Do you think that car would roll down faster or slower? Yeah, slower, wouldn't it? Okay. If it was 90 degrees, it would be like pure free fall, wouldn't it? Yeah, okay. Think about that. Okay. All right. Now, I do want to plug this into, I've got Excel rigged up to make us graphs, which we're eventually going to do, but let's do the other experiment, which is we're going to keep the mass of the car the same, but I'm going to change out the distance. Now, you guys know, obviously, longer distances is going to take more time to roll down. Oh, man. But we're going to nail down exactly what that relationship is. So it's the same 15-degree angle, all that stuff. That's not going to change. Okay. This time I'm going to leave the mass of the car is just 30 grams. We'll just use the empty car all the way down. 30. Okay. So check. So we've got 30 grams all the way down. Okay. How about for the distances of the car rolls? Let's go 50, 100, 150, 200, and then I can go to 220, but that's about as far as I can go because then my ramp runs out. Okay, so that's what we'll do. 50, 100, 150, 200, 220 in terms of centimeters, right? You guys get that? Okay. All right. Ooh, guy ready to go? Oh yeah, he is. I think like anime after leaving the room, like a Toy Story. I wake up like, oh, why the one? Okay, so we're gonna start from 50 centimeters. So this one's gonna go real fast. Okay, ready, Josh? All right, and 3, 2, 1, go. 0.44. All right. Okay. Ready? 3, 2, 1, go. 0.62. Okay. And 3, 2, 1, go. 0.62 again. All right. Okay. Take it to 100 centimeters. Ooh, so now we're doubling the distance. Ooh, doubling the distance. 3, 2, 1, go. 0.86. Okay. 3, 2, 1, go. 0.89. And 3, 2, 1, go. 0.69. All right. Here we go. 0.69. 150 centimeters. 3, 2, 1, go. 0.82. 3, 2, 1, go. 1.05. Yeah. And 3, 2, 1, go. 1.11. All right. Huh. So that was triple the distance that we started with. But look at that. The times are definitely not triple. They're less than triple, aren't they? Hello, Mr. Griffin. Hi, yep. All right. Okay, I'll tell you guys. Abigail, Mr. Rooney's looking for you, and this is probably gonna be the rest of the class. Okay, so grab this stuff. I'm recording this right now, so I'll put it online. Mr. Rooney, let me grab a room number here. Oh, where's my, oh, this is here. Admin support, right? You guys see Rooney on here? Here it is. Is there a room number up there? You can get it in the front office. Yeah, be able to get the room. Okay. All right. Camera 3. On that. I need this. Okay. I think we're ready. Yeah, we're good here. Okay. So we're rolling the car down. I got here's my car. Okay. So we just did 150 centimeters, right? Okay, we're going to 200 centimeters. Okay. Which I guess we sort of already did, didn't we? But yeah, whatever. Let's do it again. Right, you guys ready? 200 centimeters. 3, 2, 1, go. 1.21. Yeah. Right. 200 centimeters. 3, 2, 1, go. Oh boy. 1.39. I want to bounce around a little bit, but all right, that's some error in that one for sure. All right, 3, 2, 1, go. 1.36. Right. I've been forgetting to ask Morgan for the averages for these things. Yeah. Do you have the averages for all these so far?
I have all of them.
Okay. Yeah, let's fill these in. What's the top average?
0.56.
0.56. And if you square that, what do you get?
0.31.
What's it?
0.31.
Oh, 0.31. Okay. What's the next average?
0.81.
0.81. And the square of that is 0.66. Okay, and then the third average is
0.99,
0.99, and the square is
0.98,
0.98, right? Okay. The fourth average,
1.32,
1.32, and then the square is
1.74.
1.74. All right. Okay. Then we got one last set here. We're going all the way to 220 centimeters. All right, ready?
Yep.
Okay. 3, 2, 1, go. 1.2. 1.2. All right. 3, 2, 1, go. 1.44. And 3, 2, 1, go. 1.38. All right. Now, Morgan, what's the average of those 3 times?
1 second.
Okay.
1.34.
1.34 and
Square is 1.8.
1.8.
Yes, sir.
All right. Good deal. Okay. All right, so here's all our raw data for the experiment we just did anyway, right? Maybe I can get both in there. Okay. So if you guys at home need to screenshot that, if that could help. Okay. Now, when you guys at home upload this to Focus, which is I'm going to have to turn this in, I do want to see this in your handwriting. So, of course, write your name at the top of your own paper and put this in your own handwriting, all that stuff, right? Okay. All right, you guys ready to do these graphs in the back? Okay. Now, these graphs say we got mass versus time, distance versus time, and distance versus time squared, so we'll get to that eventually. But let's just start with the 2 ones that are pretty straightforward, mass versus time, distance versus time, okay? Okay. Now, we're going to, let me switch my camera because we're going to gather data. Okay. Make some switches here. Gonna take this ramp, get it out of the way. Ooh. Here. Okay. Now you might be able to. What the heck? You might be able to predict what. Oh, hold on. Gotta make 2 more switches. Makes sense. Put this here. This count. There. Fine. Whatever. Okay. Switch. Stop sharing. Switch over. Okay, and we are back. Right, so we need to plot this data to get some graphs, and from those graphs, we can figure out exactly what the relationships are among these variables. Now, there are a handful of graphical relationships that you'll commonly see in this class. So before we go chugging away on these particular graphs, I want to tell you the graphs that you'll see in general in this class. Right? Things to look for that are pretty common to pop up. So I'm going to draw 6 graphs here. 6 graphs. 6 sets of axes. And the 6 that I'm doing, these are not all the graphs, obviously, but these are ones that pop up in AP Physics a lot. And also it's going to cover the ones that you'll see today. All right, so you might see some data, but these could be all some kind of general Y versus X, just make it super generic. Okay. Now, in our case, we've got time ticking along, so like that would be one of the variables. So I'm just making just completely in general, Y versus X. You could have data that lines up kind of like this, and then I would say, ooh, maybe it's like a vertical line. Okay. You might have data that lines up kind of like this. It looks like a horizontal line. You might have data that lines up something like this, which looks like that. These have names that attach them too, but let's see if you guys can figure it out before I tell you. You have data that's something kind of like this, where the line of best fit might be something like this. Okay. You could have data that does something like this, where the line of best fit might be kind of like this. And then you could have something like that, where it's like, maybe it kind of bends down, sort of. Okay. Okay. So actually, these first 2 I'm going to call the same category. What do you think the category is for these first 2? Okay. Yeah, there's definitely some intercept involved. What were you going to say, Adam? Actually, you know what? If this was an acceleration versus time graph, that would be really key for that, wouldn't it? Okay. I'm gonna call this constant, right? This would be a constant, right? Or what's the relationship between the two variables? Like, how about this? Like the first graph, no, let me start the second one. With the second one is x changes. So x is getting all these different values going left to right. X is small on the left, x is large on the right. Does y respond at all? Does y care what x is doing? No. And it's the same scenario for the first one, isn't it? Y could be all different values, but x is like, I don't care what y is. I'm just going to be the same thing I am over and over. Okay? These are both no relationship. No relationship between x and y. For example, you guys saw an acceleration versus time graph that looks commonly just a flat line like this, because it doesn't matter how long the ball's been falling for. As long as you ignore air drag, acceleration is always the same number. Okay? There's no relationship between how long it's been falling for and how much it's accelerated. Okay? What's the name for this one? Linear. And if it goes through the origin like I drew it, a lot of times it's called direct, like a direct relationship. So if one variable doubles, the other variable also doubles. If one variable triples, the other triples, like that. Right? How about, look at this guy. As x is getting bigger, y is getting smaller, and vice versa. As x gets small, y gets big. What's the name for that? Starts with an I. What do you think, Jerry? Inverse. Yeah, inverse relationship. Good call. Okay. So if one gets small, the other gets big. See a few of those throughout this class. Okay. All right. Now, these last two, it looks like as x is getting bigger, y is also getting bigger, but in different ways. Okay. So for example, on the first one, it looks like if I double x, y could quadruple possibly, something like that. Okay. What do you think this could be called? Okay, I'm hearing like I say exponential, possibly. Okay. I'm aiming more towards like a power relationship. For example, the variable to power like x squared or x cubed or x to the fourth. Okay. Now, if you said exponential, that's a completely different kind of curve. But for small values that effects between like 0 and 5, it might start. They could start out looking kind of the same. They kind of bend up like this. But this is a different class. This is like 2 to the power of x, for example, something like that. Okay. You hardly ever see this in this class, so don't really look for it. But I mean, it's good to know that it exists in general. But in this class, there are a lot more power relationships, like x squared type relationships. Okay? And then, what if you see it bending down like this? What do you think? You know what? You guys are hitting the mirror image of these two possibilities, right? So if you guys are saying logarithmic, actually this does look pretty similar to logarithm, doesn't it? Right? That's kind of the flip side of an exponential. What I'm headed for is more like a root relationship, which is kind of the opposite of a power relationship. Actually, it is a power relationship, but it's like a fraction power. Right? The square root of x is the same thing as x to the 1/2. You guys know that, right? Okay. So it's like a fraction power. Okay, so these are ones to look for. We've got 25 minutes. Yeah, we got 25 minutes, right? Am I reading that right? Is this our lunch period? This is the second block? Yes. Okay, we got 49. Okay, yeah, thanks, guys. All right. Whew, we've got to have you guys to tell me what's going on here. All right. Okay, so let's figure out what these are going to look like for this particular data set. All right, now what you guys can do is see where it says mass versus time. Okay. That title tells you which variable to put on which axis. Now there's some rules about which variable should go on which axis. In general, let's see if we can hit these rules with fast. In general, which variable should go on the horizontal axis, the independent or dependent variable? Independent, yeah. So what you're directly inputting, directly changing yourself, you normally put on this axis, and then whatever variable responds to that, like the dependent variable that's dependent on that, you normally put on the vertical axis. But there's another rule that says if time is ticking along, then as a rule, you always put that on this axis, and that's what we're going to do. So we're going to follow the rule that says put time in seconds down here. We'll put mass, and well, today we're using grams on the vertical axis. And that would be also consistent with that title. See, it says mass versus time. It's always like y versus x. In this case, m versus t. So vertical versus horizontal. Okay. Later on, we'll do distance versus time. So we'll go x in centimeters versus t in seconds. Okay, you guys good there? Okay. Now, I'm going to take that data that we got and plug it into an Excel sheet to let do the graph for us. We can get a nice, really clean looking graph. Okay. Excel. No. It's done. Here. Okay. So go to graphs, clear all of this. This is just made up numbers. That's not anything. Okay. So mass as a function of time, right? M versus T. Okay. So this is the first experiment that we did. I'll plug in the mass values because those are nice round numbers. You got 30, 80, 130, 230, and 1,030. And the times were 1.20, 1.27, 1.22, 1.29, and 1.45. Ooh, okay. Guys, what basic relationship does that look like? It does look like constant time, doesn't it? Right? The time is constant, which means, is there any relationship at all between the mass and the time? No. Right? I asked you guys to hypothesize before we started, if I tag on more and more mass to the car, what's that going to do to the time? Okay? And it looks like it makes no difference at all. But hang on a minute, isn't this kind of consistent with some stuff I've been telling you guys about free fall over the last few days? You guys remember the Galileo experiment? Galileo ran to the top of the Leaning Tower, dropped heavy stuff, light stuff, and it all fell at the same rate, didn't it? Yeah. So if I put this on an incline, it's just under the influence of gravity, well, some component of that ends up being the sine component. I'll show you guys later, a few weeks from now. Then, it turns out that mass does end up making no difference. Right? Now, we haven't addressed in this class yet why mass doesn't matter, but at least at this point, you know that it doesn't. You know it from what I told you over the last few days, and you also know it experimentally now at this point. Have I been sharing my screen? Sorry guys, online, let me share my screen real fast. Right. So bring you guys up to speed, also for the recording purposes, right, I just plugged in our data, right? I'm looking at N versus T, and it looks like this correlates like that. Right? So let's make that graph. Right? So I'm making it myself while you guys are making it. Right? So I'm going to scale the mass up to like about 1,000 grams. Right. Thank you. Right. Yeah, so there's a lab paper on your desk, just fill in these graphs as we're going along, and you can grab the data from the recording later on. Okay, okay, so we go 0 here. Let's go. Right. Let's call this like a. Okay, so 0 scale the vertical like up to at least 1,000 because we had some of those a little over 1,000 at one point. Okay. But the times, maybe I'll call it. See, 1 times were pretty consistently about 1.2 seconds. So I'll go like 1 second, 2 seconds, right? And but it looks like no matter what the mass was, and most of them are kind of hovering around 100, right? The time was consistently hovering around 1.2. So tell you what, as long as you have your axes scaled and you have the dots pretty close to where they go, and you're looking at exactly where they go with that graph, right? Then that'll be fine, full credit. 4, 5 is right about here, over 1,000. Right. You guys see where those 5 dots are? Okay. So we flip over and show you guys the graph that I just made. Right. So if I plot those 5 points, looks like that. The line of best fit is basically a vertical line, which is no relationship. Okay. You guys good there? Okay. So flip back over to Excel, present screen to share. Okay. Now I'm gonna. So everybody has the N versus T graph, right? Well, pretty close to that. If you have your axes scaled and labeled and the dots about there, you have a vertical line best fit going between them. Okay. Really do a line best fit. Add trim line. Ooh, look at that. It's pretty much vertical, isn't it? Okay. Next, X versus T. So plug in. Now the distances went 50, 100, 150, 200. And 220. Okay. The corresponding times went, let's see, 0.56, 0.81, 0.99, 1.32, 1.34. Right? Ooh, look at those points. Okay. So X versus T graph on the back. I'm going to make it while you guys are making it. So right now we're all making distance versus time, right? It's all going to look like that. So X scale from well, make it go over 200 because the longest distance was like 220, right? 5, 8, 9, 10. Okay. Looking at I guess if you call each notch like 10 centimeters, it goes a little bit above the graph, but that'd be right. 100. That. All right. So the times and up to, if I scale the times up to 1.5, that should cover all my times. 0, 0.5, 1.0, 1.5 seconds. Okay. They got pretty close to where they go. It's like 650. So 0.56 seconds, it was 50 centimeters. At 0.81 seconds, it was 100 centimeters. How far it rolled in 0.81 seconds? For 0.99 seconds, that was 150 centimeters. 50. For 1.32 seconds, it would have rolled 200 centimeters. 32. And then, this feels right. For 1.34 seconds, about 220, right there. All right. You guys got that? Yes? Okay. I'm gonna flip the screen and show you how mine plotted out. I'll flip back to Excel here in a moment because I want to do my best fit on that. But I got, okay. Which of those relationships does this look like, if you had to guess? Yeah, we can. Oh, linear? Ooh, okay. Got it. Maybe it's a candidate for linear. Okay. Now, here's the thing about linear, okay, is if I drew a line of best fit between these, and I assumed it was a straight line relationship, okay, would this have a really big negative y-intercept, right? And then if that's true, like, because it would, wouldn't it? Wouldn't it like cross way down here, right, in negative territory? How would you interpret that? That means at time 0, like if I just let the car up to the first stand, it's like I wouldn't have to jump backwards on the track. That's how you would interpret that, right? Does that really make sense? Is that what's going on? No. So it's probably not linear. It's probably one of these, because we only have 5 points. It's probably one of these other ones in disguise. So if it's not linear, what's it probably? Yeah, Jay? Power, something to do with power, right? Now, we don't quite yet know what power. You know, let's say we're cavemen. We're just doing this experiment for the first time on Earth. Is it a third power, a fourth power, or a second power? Okay. Now, you guys know it's probably going to be something to do with like a second power, right? Like a square rule, right? But let's figure that out. Okay. And that's common to happen because this would be something that shows up in later labs this year too. Because look at these 4 points, right? Like if you threw out this guy here, the origin, they look pretty linear, don't they? Okay, be careful. It's actually part of a power relationship there. Okay. So flip back over to Excel, present screen to share. Okay. See if I do, I'll show you guys too. If I do add trend line, if I were to assume a linear relationship, that, what's this? No, I don't need your help. Get off. Then, actually, I do want to add the equation. Okay. Then I have a huge negative intercept. Look at that negative 65. That means that like the first nanosecond after I let the car go, it jumps back 65 centimeters. It doesn't make any sense. So it must not be linear. It must be something. Let's try a square relationship. Now, here's where I'm going to show you a really tricky math trick. So flip back over to projector. If linear doesn't quite work. What if we suspect that it might be x versus t squared? Something about that, which is about what's leading to this last graph, right? Okay. You guys ready for a really tricky trick? Okay. And this is called linearization. I'm about to show you guys linearization. Okay. Draw a couple of axes. First do, you know what? I'll stick with the variables that we have. Let's do x versus t, right? And let's assume that comes out to some kind of parabola, which it will. It'd be something like something to do with kt squared, right? That could be a parabola, couldn't it? X equals kt squared, right? Where k is like something. Right? Now, if we suspected that this was true, that it was specifically a parabola relationship, so x is directly related to t squared, what we can do is we can linearize this. And the way we can do that is to graph not x versus t, but x versus t squared. And if our hunch was correct that it is a parabola, then this would have to line up in a straight line, wouldn't it? Right? Where the slope of this would be what? Whatever this k was, right? Wouldn't that be that? And this could still be x is equal to some kt squared, right? But now it would be lined up because we're not graphing x versus t anymore. We're graphing x versus t squared. You guys see that trick? Right? How many guys have ever seen this before? Have you guys ever seen this before, this trick? Who's ever seen this? Ooh, a couple of you guys have? Did you guys do this in a, like, honors physics or? Okay. All right, so if you had honors physics, you've seen this. Right? If you've never seen this before, AP really likes to do this. So you're like almost for sure, actually pretty much for sure, going to get AP questions related to something like this. Okay? You guys ready to apply this? Right. So let me flip back over. That's why we had that squared column. You guys remember I was asking Morgan to square all the numbers? Okay? Now I plugged it in so that Excel did this automatically. It's going to bring us to the third graph. See where it says x versus t squared. Okay. So I had Excel automatically square all the time. Look at that. Look at all those points. See those points pretty well lined up into a straight line? They sure do, don't they? There's a line that doesn't fit. Whoops, I want to put the equation on here. Add trend line, graph the equation. Right? It's in the form of y equals mx plus b, but remember, it's not x versus time, it's x versus time squared. Right? It says, there's the equation. You guys see that y-intercept of like 10? For our purposes, that's actually extremely close to what? Yeah, 0, right? Are we basically assuming this pretty much goes through the origin? So that plus 10 doesn't really count, right? Or maybe it means something, but what we care about is the slope of this. So y equals 118x, something like that. Guess that? Okay. So that is the last graph. Okay. So the one says distance versus time squared. So on the vertical axis, put distance in centimeters. On the horizontal axis, put not time, but time squared, which is in square seconds. Okay. And well, there's your table of data. So let's see. Time squared goes up to one base number looks like 1.8, I think. So 1, 2, 0, 1, 2 square seconds. And the distances go up to 220. So for 0.31 square seconds, the distance was 50 centimeters. By the way, I should mention that's a really nice looking graph. So you guys got good numbers. Yeah, so Joshua, definitely good job with the on the stopwatch. So for 0.66, it was 100 centimeters. For 0.98 square seconds, it was 150. For 1.24 square seconds, it was 200. And then for 1.8 square seconds, it was 220. 20 is right about there. Okay. So 118. Guys good there? Ooh, we got just enough time to do exactly what I want to do. Okay, you guys ready? Okay. I'm gonna flip my screen. Okay. Show you guys my work here. Here's the line of best fit. Zip. Okay, let's call this x equals. And you guys remember the number from Excel? It was like 118 times time squared. Remember, t squared is thinking like your independent variable in terms of this graph, right? Okay. And this number 118 has units of, what are the units on this guy? Centimeters per second squared, right? Wouldn't it have to be centimeters per second squared? Because if you multiply by square seconds, that brings you back to centimeters, doesn't it? Right? This is the equation of this line, 118 centimeters per second squared times time squared. Okay? Now, do you think this 118 centimeters per second squared has something to do with the acceleration? That is an acceleration unit, isn't it? But it's, I'll tell you what, it's not the acceleration itself, but it is you can figure out the acceleration from this. Because, guys, you remember this? X equals, let's go back to knowing that you guys know physics. You guys know this is true, right? X is 1/2 AT squared. Could you take that 118 and probably equate that to that and solve for A? Could you guys do that? Figure that out? Right. So here, let's finish this off. Distance at, what was our angle? 15 degrees is, right. So write the equation for distance. How's mass going to enter into this? It's not, right? It's no, because remember, there's no relationship with the mass. So are you going to have m in here as a unit? Or sorry, as a variable? Nope. Right? But I bet the answer is probably written right in front of you, right? Right. So here's your homework between today and tomorrow. Right. So you guys remember AP Classroom, multiple choice is due Thursday. I mean, you guys have known that, right? In fact, some of you guys may have turned it in already. Right? That FRQ, the multiple choice questions due Thursday, we're going to delay to Friday. I think that's going to be our Friday activity. Right? So I'm going to change the due date on that. So you probably want to read it ahead of time, but don't worry about it yet. Right? You guys see what we do with that in class. And finally, I want you guys to solve for the acceleration of this toy car, for this particular lab, which has something to do with this stuff going on, right? From Excel, right? So yeah, that's a great question. So the question is, where does the 118 come from? Right, we've got about 50 seconds in here, so yeah, that's how to answer that. Yeah, I had to find the best fit and had Excel come up with the equation for me. And, yeah, there's like a whole statistical crunching that it does inside its little computer brain. Okay. Yeah, so that was a great question though, because I bet some of you guys were asking that. Okay. Who has any questions about anything? Content? Think by tomorrow? Right. And then, I want to remind you guys too, for the homework, some of you guys want to do the redo. Some of you guys need to do the redo for yesterday's stuff. So, well, add that down here. Right, so redo, and for that, do number 7 and number 8 from the linear motion, right? If you need to. If you did exactly what I did this morning, then you're fine. Okay, the bell should have rung right now, so that is the end of class, and I will see you guys on Wednesday. Yeah. Good job. I was glad we got really nice looking graphs and numbers. Yeah, have a good day, guys.